I expect that this video will be of a lot more interest to a lot of people because we will be implementing PID controls on this aircraft. The last time, what we managed to do is basically just make it go up, and that's it. Let's do a quick recap from the previous video. So first we declare our arrays, and these arrays contain the thruster facing directions, and later we will also declare arrays for the PIDs for each of the thrusters. Then we sort the thrusters, so we get their facing directions and so on, and then we use a dot vector to go in a desired direction, which in this case is just up. And using that dot vector we get the drive fraction, which we feed to specific thrusters. For now, just think of this as a black box if you don't quite get it yet. If you want to try to understand this better, then please go to the first video. Okay, so if we change this, let's say 0, it's gonna stop firing all the thrusters and it will start going down. So as you can see, our altitude is decreasing. You can see our altitude on the right side of the screen. Okay, and now if we do something like 0.1, it's gonna increase slightly. Still not quite enough to generate to start going upwards, but now okay, if we do, this is probably going to be enough. Let's see. Okay, basically hanging in the air. So point is, we can modulate that value to start going up or down. So now we're gonna use a PID control to change that value so that we stay at some altitude set point. Okay, for our PID control we need the altitude error first, because that's what we're going to be controlling, and the altitude error is our altitude set point minus our current altitude. And here our altitude set point, let's just make it 30, and then we need to find our current altitude, and this is how we can do that. Get local position, we go to self-awareness, construct position, and then we get local. Apply. And now we declare an error for the controller, which will be our altitude set point minus h. And then we have h, and I will call it PID-H for PID height, which is some proportional coefficient times our altitude error. So the implementation of the proportional term of the PID is very simple, and let's make this just 1 for now. And let's see how the aircraft responds when we feed this value to our drive fraction. But the thing is, right now this value can be both positive and negative, but the only valid drive fraction is from 0 to 1, so we need to limit this from 0 to 1. Okay, that should do it. And now we should see result. Oh, okay, something's still wrong. Oops. PID. Here we go. Now it should work just fine. Yeah, it's not firing. And now you're gonna see we're gonna drop below 30 and it's gonna start to fire. Here we go. And now we have very crude proportional control. And as you can see, I'm probably making you sick right now, but yeah, we stay mostly in one spot, and no matter the orientation, we still stay in the air. We are going to change our approach for a more general one. Instead of just controlling the altitude set point, we will control the aircraft by setting a point in space and trying to get to that point. This will get rid of the drift that the vehicle has while idle. So right now it's being controlled by the control scheme I'm describing. So it has no drift and it just stays nicely put. But yeah, there are other ways of getting rid of the drift, but I think this is the most elegant because it's very simple to change the set point to be our target, and then we can track our target like so. So basically it's gonna this, and now the set point changes to the target location and it just tracks the target. And yeah, and it's just a more elegant solution in my opinion. Okay. And then it changes its set point to its last location plus its set point altitude, and it just stops like this, which is a neater way of doing this than the way I had before. You could also stop the drift by making the thrusters, by having an equal amount of thrusters on each side. You can have an additional PID control that controls the drift. If you don't have an equal amount of thrusters on each side, you can just scale their outputs and stop the drift that way. So some things remain the same. So this is the proportional gain. All of this remains the same. But now here we need to make some changes. So this is our current point in space. And we want to save this point and remain at it. So we're trying to save our current position and just remain at it as the code continues running. And we need to set our current position y component to our altitude set point because that's what we're aiming for. Okay, now we need to define our PID. So we need to set this value to something. And this next part will get a bit abstract. If you want to understand why this next part works, I highly recommend watching the first video and watching the dot vector idea. But here is what we are going to do. Okay, so now we define a position error. Basically, this is the vector pointing towards our global position set point. It is convenient to use the normalized vector, not the whole vector, because what we need is just the direction. Like, we don't care about the magnitude information, we just need the direction for our purposes. And then for our PID value, we have, for now, let's just use the proportional control again. So we have our proportional coefficient Kp times, okay, and then we have the same limit as before. The only valid inputs are from 1 to 0, so we just limit it this way. And we can have this outside our for loop because the error will be the same for all the thrusters. So now we need to apply this error in the appropriate direction, and we use our dot vector idea for that. And this is how we do that. This is how we find the appropriate direction. So we dot our global forwards facing array of our thrusters with the direction we want to go in. And the direction we want to go in is this right here. So it's the normalized position error vector. So that's the direction. Actually, before I do this, just so that it's more instructive, show you how this works. So as you can see, right now it's not modulated at all, and the PID control will make this more controllable. Now it's just firing towards the position without any control. But as you can see, the idea works. Okay. And now we just need to scale this with our PID. And here I have limited that drive fraction again. Technically I could just limit this, but the thing is I don't want any negative values here to confuse anything. So I just do this, and then I do this. And then of course we just set our drive fraction for everything. Okay. And now we can use our proportional to make this calmer. Okay, this might be way too small. Yeah, it's way too small. Okay, let's make this 0.1. So now it's not as violent. Okay. 9, as you can see, we're a bit below. Let's change this to 50. We don't go up. Because we don't switch, but we should. Interesting. Yes, I haven't declared this yet. It's going to be nice and calm. And we can add integral control later, and we can make up the error so that we're at 50. Okay, so this is quite nice, but we're not done yet. There needs to be more functionality here. But now we have all of this drift all over the place, and I want to get rid of that movement, this sideways movement, and that oscillation. And of course, the way of doing this, the way we can do this, is by introducing derivative control. So we need to add a derivative term. But the thing is, like, this drift is not well described by our error to our altitude set point, but it is well described by our velocity vector. So now we need to add an additional control that takes in the velocity vector and tries to drive it to 0. And that's how we will get rid of this drift. Sounds complicated, but the implementation is not that hard. So it's very similar to what we've done already. We have our velocity. Then we have our velocity normalized. I believe we might end up not using this at all, so I might delete it later. This is our oscillation error, and that's going to be equal to the magnitude of our velocity. So it's a very similar idea to our previous one. So our derivative will be our oscillation error minus our odd oscillation error. And this is not very rigorous. Like, this is not an actual derivative, of course, but this captures the functionality. This is all we need to capture the functionality of the derivative. We just need to save this RD value now. We can do it right here, actually. And now we have a separate PID. So this is not a PID, it's just a proportional control, so technically it's just P, but I'll call it PID. So we have some we have some coefficient for our derivative times our derivative. That's our oscillation PID. So now we've defined the oscillation PID output. It's just a derivative controller. So again, technically this is just D. I'll call it PID because why not? We need to do the same things as before. To enforce valid values, we will limit this value to be in the same range as this previous one. You just need to rename these variables here. Okay, that's simple enough. Now we need a new drive fraction. So this is like a separate controller. We will call this osci for oscillation. Then this remains the same. But now, instead of the normal error, we need to use the velocity errors. So here, we need to use this. And I've tested this before, and I know that we need to use negative values. And of course, we also need to rename these. Okay, now we will limit the drive fraction in the same way we've done before. For the PID, remember to declare this value. So declare KD somewhere. Right now I have it at 2. Okay, let's play again. Okay, nothing broke. That's great. Now we add df osci, and hopefully it's going to work. Let's see if we stop. And yep, we have stopped. But I think I'll actually increase this slightly, and it's gonna dump us even more. Okay, but now we have an issue where both of these values can be equal to 1. So the drive fraction from our position error could be 1, and our drive fraction from our oscillation error can be 1. So total possible output is 2 right now, which obviously is not a valid value, so we need to somehow make sure that we never exceed the maximum value, which is from 0 to 1. So what we can do is, we can make sure that the total is always less or equal to 1 by simply doing this. And this is also desirable because right now this will dominate. So the controller will first make sure that we are in the right position, and only once this error is small enough will it switch to slowing us down and stopping us. And you can see that it's doing its best to just stay in place. Right now the values are not optimal, so it's doing this stuff. Something is oversaturating the controller, so it's getting really spazzy. Okay, I'll try to tweak the values, so be with you in a second. Yeah, this seems to work reasonably well. Yeah, I'll leave it as like this. And it turns out we don't even need the integral, because as you can see, we're right at 80 meters where we want to be, right at our set point. So we don't even need the integral term to make up the error, since the proportional is large enough that we're basically at our set point anyway. Yeah. Okay. The next time we will track a target, and that will be the last video. So see you next time.